Alright, continuing on, we're going to start talking about standard conditions. So, because the volume of a gas varies with pressure and temperature, chemists have agreed on a set of conditions to report our measurements so that comparison is easy. Essentially, if you don't really care what the pressure and temperature are, people will do experiments at what we call STP, standard temperature and pressure. So a lot of this is mainly useful for making tables and things like that. Most of the tables that you'll come across where there's lots and lots of data for lots of gases, most of those data tables will have been measured at STP, standard temperature and pressure, which is 1 atmosphere. Oops. Got to turn on my, here we go. 1 atmosphere and 0 degrees C or 273 Kelvin, which again, we need to use that temperature in Kelvin for any calculations that we're doing. So if we plug those numbers into the ideal gas law, so we plug in 1 mole, just because we want to get data for just a single mole of material. So for example, in this case here, we're trying to find the volume of our sample of gas. So we plug in 1 mole. The constant is always the same. We use the standard temperature and pressure, 273 K, 1 atmosphere of pressure. What we get is that a mole of gas at STP, standard temperature and pressure, will have a volume of 22.4 liters. And what's interesting about that is that this is the case for any gas that we come across, because again, remember, the ideal gas law does not discriminate for one gas versus another. It doesn't care what is in the gas. It doesn't care what the gas is made of. All it cares about is how many particles of gas are there. So you can have something that's relatively large, like xenon. It's a large atom, xenon is. It's bigger than even the molecule of methane. And it will have the exact same volume if you have a liter, or a mole of it at STP as something that is really tiny, like helium. Because all gases behave practically the same way. Again, it is a little bit different. Not all gases behave exactly ideally. But for our purposes, we're going to pretend like they do. So no matter what the gas is, if you have a mole of it at STP, it will occupy 22.4 liters of space. This is what we call the molar volume. It's the volume that a mole of a gas occupies. So, solving the ideal gas law gives us this number. What makes this, another reason why this is kind of handy, is oftentimes if we're trying to work out stoichiometry and things like that, which we'll do in just a little bit, we can actually use this molar volume as kind of a shortcut. We can use it instead of solving PV equals nRT to try to work out how many moles of something we have. If we know we're at STP, we can just shortcut that whole equation and just say, well, if I know I'm at STP and I know what the volume of my gas is, I know that for every 1 mole, I'll have 22.4 liters. And so this will come in handy later on when we do a little bit of stoichiometry with gases, using this molar volume for any gas, because again, it works for anything. It doesn't matter what the gas is. So while we recognize this, that it doesn't matter what the gas is in terms of how many liters of space it will occupy for every mole, one thing that is different going from one gas to another is the mass of that gas. If we go back here, I mentioned that xenon is much bigger than helium. It's much bigger. The atoms of xenon are significant. I don't have it right in front of me, but I want to say xenon is 150 or something like that. Maybe not quite that big, but it's a pretty large atomic mass, whereas helium is 2. So, well, I guess 4. It has 2 protons, so it'd be 4. So this is much bigger atom than these. Xenon atoms are much, much bigger than helium atoms. So while the number of moles is the same and the volume is the same, the mass of the sample is not the same. And so because of that, the density of gases are not the same. Every gas is going to have a different density, and this is pretty much the only thing we're going to see for the rest of this chapter, or for all of this chapter, where we do actually care what the gas is. Everything else, we don't really care, because gases all behave the same way. But when it comes to density, because the actual particles have different sizes, we do actually care what the gas is. So, when we're trying to find the density of a gas, thankfully there's a pretty easy way to do that. If we know what the gas is made of, if we know if it's nitrogen dioxide, for example, it's pretty easy to actually calculate the density of that gas. All we have to do is this. The density of the gas is going to be the molar mass of that gas, which we know how to find that. It's just from the periodic table. We've done that dozens of times at this point, if not 100 times. So the molar mass from the periodic table divided by the molar volume, which is 22.4 liters per mole. And that's this right here, 22.4 liters for every 1 mole at STP. So we do have to have our gas at STP for this to be the case, but we will have our gases at STP most of the time. And so the way that works out, the molar mass, so for helium, for example, it has a molar mass of 4 grams per mole. It has a molar volume of 22.4 liters per mole. Those moles cancel each other out, leaving us with grams per liter. And that is a unit of density. We're used to seeing grams per mil, but for gases, just because they're so low in density, we usually use grams per liter instead. And just because the units work out that way anyway. So helium is 0.179 grams per liter. And nitrogen, which is a larger atom, about 14 times larger, it correspondingly has a larger density. It is 1.25 grams per liter. So anytime we're trying to find the density of a gas and we actually know what the gas is, we have the molecular formula of the gas, all we have to do is just take its molar mass and divide by 22.4 liters per mole. And that will give us the density. If we're trying to incorporate density into the ideal gas law, the way that we can do that is to start off with here, we're going to do a little bit of algebraic rearranging. So we're going to take the normal ideal gas law, we're going to divide both sides by RT and V, and so that'll end up giving us this. And if you notice, this is the molar density, the number of moles per liter. Moles divided by volume. And if we take moles divided by volume and we multiply it by the molar mass, so the grams per mole of whatever gas that we're interested in, that will give us grams per liter, which is the density we're actually looking for. And so what we've done here is we've shown that if we take the ideal gas law like this, and by the way, if we're going to multiply it by the molar mass, we have to multiply the other side by the molar mass as well. We can't just randomly stick in a molar mass anywhere we want. So we're multiplying both sides of the equation by the molar mass. What that ends up doing is this molar mass times the molar density just turns into the density, the grams per liter density, and then on the right side of the equation we have the pressure times the molar mass divided by the constant times the temperature. So what this tells us is that the density is directly proportional to the molar mass, and not only that, this equation is going to give us a nice easy way of either finding the density if we know the molar mass, which actually there's an easier way for us to do that back here, but more likely It's going to give us an easy way, if we know the density of the gas, if we know how many grams of gas we have for every liter, that will allow us an easy way to find the molar mass for that gas. And it doesn't actually have to be at STP for us to do this either. It could be at different pressures and temperatures, which is the actual really nice thing about this equation. Because if it was at STP, then pretty much just go back and use this one. It's easier. But if it's not at STP, then we will use this equation. All right. So this is just talking about how this is one way to actually find the molar mass of unknown substances. If it's something that you can turn into a gas relatively easily, you can measure its weight, turn it into a gas, see what volume of space it occupies, and you can actually work backwards and find the molar mass of that particular molecule. So in this example here, we actually know what the gas is, but what we're trying to find is the density, and we cannot use this because we're not at STP. If we were at STP, then yeah, we could just plug in the molar mass and we're good to go. But because we are not at STP, we can't do that. So go ahead and pause the video and try to work out this problem on your own, and we'll work it out together. Alright, so we're trying to find the density. And the equation from the slide back here tells us that the density is equal to the pressure times the molar mass divided by RT. So I need to find all four of these things. Now, most of these are actually given to me in one way or another in the problem. So first of all, it tells me that the pressure is 755 millimeters of mercury. I do need to change that to atmospheres. It's going to be 0.99 something. Let's go ahead and do that. So that is 755 millimeters of mercury. And if you go back and check, 760 millimeters of mercury is the same as 1 atmosphere. And so that is going to end up being 0.993 atmospheres. All right. So we know our pressure, and we have it in the correct unit. Temperature, we are told that we're at 125 degrees C. We're just going to add 273 to that to get, let's see, 398 Kelvin. We know what R is, because it's a constant. The molar mass is not directly given to us in the problem, but we're told that it's nitrogen gas, which is not this. Remember, nitrogen gas is N2. Nitrogen is one of the 7 diatomic elements. So nitrogen gas is N2. A single nitrogen is 14.01. And so our molar mass is going to be 28.02 grams per mole. All right, we have everything we need. So the density of our gas is, let's see, 0.993 atmospheres times 28.02 grams per mole divided by 0.08206 liter atmospheres per mole K times 398. Okay. So once again, the units will work out here. Atmospheres cancel. Let's see, moles cancel. Kelvin cancels. leaving us with grams over liters, which is good. And if we do the math, we get the density of nitrogen at 125 degrees is 0.852 grams per liter. What you might notice is significantly less than the density of nitrogen gas at STP. So at standard temperature and pressure, N2 is 1.25 grams per liter. And if you heat it up, and it's still at pretty much 1 atmosphere there, but if you heat it up 125 degrees, it becomes almost half, not quite half, the density. Which is why hot air balloons float, by the way, again. Because if you heat that gas up, the gas inside is much hotter than the gas around outside of the balloon, and the things that are in that have a low density will float in things with a higher density. So that is why the hot air balloons rise up in the air. All right, let's do one more of these, I believe. Yeah, so one more. So again, go ahead and pause the video, read through the question, see if you can solve this one on your own. All right, so first of all, ignore that number, obviously. It's not 5.8. It's from an old book. But if we look at the question here, we are asked, a sample of gas has a mass of 0.311 grams. Its volume is 0.225 liters at a temperature of 55 degrees C and a pressure of 886 millimeters of mercury. Find its molar mass. All right, almost everything in this problem is in the wrong unit. Everything except for the liters. The grams here, well, I guess grams we actually do want to leave in grams because the density is grams per liter, and that is going to be, go back and look at the equation here, the density is equal to the pressure times the molar mass divided by RT. So we actually don't want to change that into moles. We want to leave it in grams. So we have our grams and our liters, which will allow us to find the density. We're given the pressure, which is 886 millimeters of mercury. So to get that in atmospheres, we'd want to divide it by 760, and I'm just going to go ahead and do that without writing it down. So 886 divided by 760 gives me 1.1, let's see, 17, we'll say, atmospheres. And then the temperature is going to be 55 plus 273, which is 328 Kelvin. All right, so we have our temperature, we know the constant, we know the pressure, and we were given enough information to find the density. So if we go ahead and plug in what we know, we have 0.311 grams for every 0.225 liters. The pressure is 1.17 atmospheres. That is going to be multiplied by our unknown molar mass. And then we're going to have 0.08206. I'm just going to trust that you all believe me that the units are going to work out there, because I don't want to write all those in again. So then you have 328 Kelvin. If we do all this mess of math, so we're going to have 0.311 divided by 0.225 divided by 1.17 multiplied by 0.08206 multiplied by 328. So again, did the math over here and then multiplied by everything on the bottom to essentially move those over, and then divide by everything, which is just one thing on the top here. And what that leaves me with is the molar mass is equal to 31.8, oops, ran out of space there, grams per mole. Alright, that will be it for this video. I will see you in the next one when we will talk about mixtures of gases.